Hello viewers, I am Bikshamaiah, Assistant Professor of Physics from Government Degree College for Women, Nalgonda. I am going to deliver a lecture on paramagnetism in this video. So we see the Langevin classical theory of paramagnetism. Langevin considered a paramagnetic gas containing n atoms per unit volume, each atom having a permanent magnetic moment mu. So the mutual interaction between the magnetic dipoles was assumed to be negligible. So here the interaction is considered only between the magnetic moments, atomic magnetic moments, and the external field B. But there may be interaction between the magnetic dipoles. So that is very weak. Therefore, so that is neglected. So that was the consideration or assumption taken here. So after that, so if the paramagnetic gas is in thermal equilibrium, the potential energy of each dipole in this position is given by the energy, interaction energy E is equal to minus mu dot B, mu bar dot B bar. Mu bar is the magnetic moment, is a vector quantity, and B is the external field. It is a dot product. So now we are getting this E is equal to mu dot B cos theta. So it is the interaction energy expression. Now, so it is the diagram. So it is the field direction B, which is in brown color, is the direction of magnetic field, or we can say the field axis. So here mu, we are considering, okay, so we are considering here the magnetic moment of the atom is oriented in this direction, and it is making some angle. So here we are considering a three-dimensional material gas. So we are considering the magnetic moments, a range of magnetic moments which are making angle with the field axis theta and t plus d theta. So that means, so we are considering many magnetic moments in this region, in this d theta region, which is making angle at starting theta angle and ending theta plus d theta. Okay, with this annulus region we can say, so if we see from side view, so just like this, so this is the angle, so actually it is the solid angle. So a limited range of solid angle we can uh, call it as d omega. If total solid angle is omega, and d omega is the a particular annulus region solid angle. So so it is the angle of what semi angle, only semi angle with this field axis. So the same angle is made in this direction also. We are taking in one direction, and if we rotate it in 360 degrees, it covers the cone, covers the cone. So it is the 3D view. So here magnetic moment is identified, and we are resolving the magnetic moments. Okay, if it is mu, and it is suppose the particular magnetic moment is making some angle theta with a vertical, that means field axis, then so we are resolving with respect to this, and if we draw one line here, and it is the perpendicular line, perpendicular line. So from this triangle, the triangle this I am identifying, so from this triangle, it is rectangular triangle, and it is theta. and this one is adjacent side. So it is along field axis adjacent side, and it is opposite side. So therefore we are resolving the component. If it is mu, and it is mu cos theta, and this one is mu sin theta, mu sin theta. So here we can see it is identified. This component is mu cos theta. Along this direction is mu cos theta. Here it is shown, and in this direction mu sin theta. So it also present in this direction also. So if we resolve this magnetic moment, and it is mu cos theta, and it is mu sin theta. So the perpendicular, these components, the components perpendicular to the field in both directions, that means around the axis, cancel. They cancel each other. The perpendicular components cancel each other, and or we can write also just like this. So it is mu sin theta in this direction. So in that way, it is the perpendicular components cancel each other. Only the components along field direction survive. Those components are mu cos theta only. Mu cos theta. Okay, right. So now we see the derivation part. Since it is purely mathematical, I am taking from my writing. So instead of a slide. So using Maxwell-Boltzmann distribution law, so the number of magnetic dipoles, so the number of magnetic dipoles having this particular orientation is proportional to this factor e power minus e by kt, the exponential of minus e by kt. So we have seen just before the magnetic moments which are making some angle theta with field direction. They are interacted by the energy E is equal to minus mu b cos theta, mu dot b, mu b cos theta. So the number of such magnetic poles depends on the energy, this factor, exponential factor of energy. So therefore we are writing that energy expression in this Maxwell-Boltzmann distribution law. So here instead of E, I have written here mu b cos theta, and right, MC, okay, right. So it is E, and it is mu b cos theta, and minus minus plus. So it is, the number is proportional to e power mu b cos theta by kt. Here k is Boltzmann constant, and T is the absolute temperature at which the gas is present. Now, according statistical mechanics, the number of dipoles having axis within the solid angle d omega lying between halo cones of semi angles theta and theta plus d theta is given by dn. So dn, the number of dipole we are taking as dn, so which present in that particular direction, which are making angles theta and d theta with the axis. So that number is dependent on, or that proportional to, so the earlier factor and into d omega, that solid angle. If the solid angle increases, obviously the number increases. This is the directly proportionality, and this was exponential dependent. Now if we remove this proportionality, we get some constant, and the solid angle is 2 pi sin theta into d theta. The d omega is equal to 2 pi sin theta into d theta. So here it is simple one. arbitrary constant. So we should remember this k and this k are totally different. Otherwise, we should keep this constant as somewhat else. Okay, like C also. We can keep this as C. So each dipole contributes a component of magnetic moment mu cos theta along B to the magnetization. So we have seen this in the figure. So the perpendicular components cancel each other, and components which are in field direction, that is mu cos theta, only contributes to the magnetization of the material. Okay. So therefore the number of atoms per unit volume. So it is considered in the starting itself, the number of atoms per unit volume is capital M. So therefore, so the total magnetization, that is equal to the magnetic moment due to all atoms. Therefore, we are multiplying it. So M is equal to, since it generally according our definition, magnetization is magnetic moment per unit volume. Per unit volume. From here we are getting magnetic moment only, and here some number. So volume is hidden in this number. Since whenever we take this, we are defining in this way. It is the number per volume. So therefore, magnetic moment per volume is the magnetization. So magnetization due to all atoms, therefore N. So just like that. So it is the number per unit volume and into magnetic moment. Therefore, we are getting the total magnetic moment per unit volume. So it is a magnetization due to all n atoms. Now, so mu is magnetic moment, which is a fixed quantity, constant. We are writing it outside. We have to calculate the average value of this or the expectation value of cos theta. So over the entire range, over the different angles. So therefore, so so we are calculating this. So we have seen, right. So we have seen earlier, this was a field axis, and it was our mu, right. So it was our mu direction, and it was B. Okay. So it was B direction, and it was the angle. So it was the angle theta. Okay, just like this. So in order to cover the all magnetic moments in the solid, sorry, in the gas, considered gas, so we are, so we are, so we have drawn just like this. Okay, right. So we have considered in this direction. So we have to calculate for all directions. Therefore, we have to just like rotate the vector in this total direction. So for that purpose, we have to rotate the vector in this totally all directions from here to here. It covers, if it is in field direction, it is the field direction. So 0, and in this direction totally 180. So therefore we are integrating from 0 to pi. So 0 to pi. So therefore, so 0 to pi mu cos theta dn. So we have written, and since we are saying it as average, so the magnetic moments due to all atoms divided by the total number of atoms. So in that region, so the total number of atoms having that particular mu. So if it is only the total number of atoms, the integration dn, there is chance for getting capital N. So it is not that. So it is the number of atoms which are having mu magnetic moment. So the dn are the number of atoms which are having magnetic moment mu, and they fall in this in angular range. So they should fall in this angular range 0 to pi. So therefore we are writing 0 to pi into dn. So that value as directly we are substituting dn value where we have got dn value here. So therefore we are writing the similar dn here and in denominator and numerator. It is simple mathematical calculation. We are substituting the dn value, numerator and denominator with this, and there was cos theta, and here we are getting sin theta, d theta, and exponential factor. So here variable is only one, that is theta. We have to keep the terms or functions which are with theta, and we write the other quantities outside the integration. So to simplify this integration and these two integrations, we are substituting some variables. So, so those variables are mu b by kt is equal to x, and cos theta is equal to y. So it is for simplification of integration only. So later, wherever we come across with these variables x and y, we substitute the related quantities. We give the physical explanation uh, according these parameters only. So it is only for simplification of the problem. So therefore, cos theta is equal to y, then integration on both sides, sorry, differentiation on both sides. So minus sin theta into d theta is equal to dy. So we see the here the limits are in theta variables. Therefore, here the corresponding variable is y. Therefore, we should convert these limits into corresponding y values. Therefore, if theta, the lower limit is 0, if theta is 0, so y is equal to cos 0, that is 1. If it is theta is equal to pi, y is equal to cos pi, so that is minus 1. So in that way, the limits are from 1 to minus 1. The lower limit is 1 and upper limit is minus 1. So we are substituting these values. So here, so m is equal to, this m is equal to n mu is there, n mu is there. So 1 2 minus 1, 1 2 minus 1, here it is written. So cos theta is equal to y, therefore cos theta is equal to y, and mu b by kt is equal to x, and cos theta y e power xy, here e power xy into sin theta into d theta is equal to minus dy. So therefore we should write here minus dy. Okay, and e power xy dy is similar thing. So if we do this, okay, we do this. So if we simplify this integration, we get this equation e power x plus e power minus x divided by e power x minus e power minus x minus 1 by x. So this one is cot hx, hyperbolic function cot hx minus 1 by x. Okay, this combined function cot hx minus 1 by x is called Lagrangian function. Lagrangian function. So, so we are representing with that L of x, Lagrangian function. So there are two possibilities, two cases. So x is less than 1. That means mu b is less than kt. So that means the magnetic interaction energy is smaller than the thermal energy at room, the thermal energy. Okay, so if the sample or gas is existing at some temperature, it possesses some thermal energy also, and the interaction energy. So we are seeing what happens if the magnetic interaction energy is smaller than the thermal energy. So it is the case. In other case, we see mu b is much greater than kt. we see in that case also. Now, in this case, at normal field strengths and ordinary temperatures, that means the field strength is weak, we can say. So in that case, so for above function, for the mathematical function cot hx minus 1 by x, so this one L of x at x is equal to 0, so we get x by 3. So that's value, we get x by 3. So x is mu b by kt, and we writing that, so we are getting mu b by 3 kt. So it is equation 2 and it is equation 1. So we are substituting this equation 2 in equation 1. So here already there is n mu. Now here we are getting mu b. Therefore n mu square b by mu square b by 3 kt. Okay. So again we are writing b is equal to mu naught h. So b is equal to mu naught h. So here we have to remember one thing. Here mu naught, they are appearing as same quantities, but they are different quantities. Here mu naught is permeability of free space, and mu is the magnetic moment. It is not permeability. So it is the magnetic moment of the gas. And it is the permeability of the gas. Okay, it is permeability of free space. So this is the quantity. So but the susceptibility is defined by magnetization per unit applied field. So therefore the susceptibility is equal to m by h, the paramagnetic susceptibility. Since the material is paramagnetic or the gas is paramagnetic, its magnetic moments values are very small in quantity. So m by h, simply by bringing this h towards LHS, the remaining quantity is this mu naught n mu square by 3 kt. It is the paramagnetic susceptibility. Okay, and we are writing. So here T is only the uh, parameter variable, so which is dependent on. There is the chance for variable. So therefore, the remaining all are treated as constant for a fixed gas. So therefore, paramagnetic susceptibility is equal to C by T. Here C is equal to mu naught n mu square by 3k. It is called as Curie constant, and this equation is called Curie's law. Curie's law. So this equation holds good, or Curie's equation holds good for this approximation. It is a equation derived when the approximation is taken this approximation. So therefore this law holds good when x is less than 1. So that is mu b less than kt. Curie's law holds good for mu b less than kt. So the second case, for large values of x. So that means mu b is much greater than kt. So mu b is the magnetic interaction energy. Therefore, high flux densities, for high flux densities at lower temperatures. So we are saying kt is low. So at lower temperatures, the function L of x, so that is equal to cot hx minus 1 by x, approaches the value 1. So approaches the value 1. So if it is 1, simply we are writing from equation 1, it is our equation 1 here, here it is there. So here we are writing 1. So then we get, so m is equal to n mu. Okay. So this one is called, that means the total, whatever the magnetic moments are available in that gas, all the magnetic moments align in the field direction. So there are no other magnetic moments to align field direction further. So that is called the saturation is reached. So therefore, so that condition is called as saturated magnetization. All atoms or all magnetic moments align in the field direction. That one is called saturated magnetization. So, so that is the maximum magnetization we can get. Now all magnetic dipoles align in the field direction. Okay, that is the thing. So it is Langevins classical theory of paramagnetism. So this says that the paramagnetism decreases with the temperature. So the paramagnetism property decreases with the temperature. So if the temperature is high, at certain temperatures, the paramagnetic substances also become diamagnetic. So we have seen in the last class the diamagnetism property is independent of temperature. So that does not depend on temperature. So and we have known that all magnetic materials possess diamagnetic property, but so these other effects suppress the diamagnetic nature. Okay, so it is about paramagnetic Lensven theory of paramagnetism. So thank you very much for watching. So please subscribe to the channel for more related videos, and please send to the needy persons. So it is the syllabus of BSc final year 5th semester solid state physics. Okay, thank you.